In my Structural Engineering Made Simple series, today I would like to talk about design of singly reinforced rectangular sections for bending. Please take a moment and read the disclaimer at the bottom of this page before we continue. Singly reinforced rectangular sections are designed for longitudinal steel bars for bending and transverse reinforcement for shear. This video explains the design for bending. In general, the procedure includes a design for the size of the cross section, the amount of steel needed in the tension area of the cross section, number of bars and the bar arrangement, and the detailing of the section. These figures show typical singly reinforced cross sections and their bar arrangement. This one to the left shows a rectangular section with closed loop stirrups. The one at the middle shows a rectangular section with open loop stirrups. And the one to the right shows a rectangular section with multiple layers of tension steel. Please notice that a minimum number of bars are provided in the compression area. However, these bars are usually not counted for in the computation for the resistance of the cross section. In seismic design and in cases where a section must also be designed for torsion, only closed loop stirrups are allowed. Here are the notations. AS is the area of tension steel. B and H are the section width and height. D is a distance showing the location of steel measured from center of tension steel to the extreme concrete compressive fiber. D sub T is a distance showing the location of the first layer of tension steel farthest out from the extreme concrete compressive fiber. dt is equal to D when only one layer of tension steel is used. F prime sub C and Fy are respectively the concrete compressive strength and steel yield strength in PSI. Mu is a factored applied moment, also sometimes called the design moment. Mn is a nominal flexural resistance of the cross section. Epsilon T is a strain in the first layer of steel, farthest layer from compressive concrete fiber. Phi is a resistance reduction factor, and rho is a steel ratio, which is AS divided by BD. Design procedure. Several design procedures are available, mostly require some type of design aids. In this video, a procedure based on trial and error is explained without reliance on design aids or design tables. In this procedure, the unknown parameters to be determined are AS, H, D, and B, and the known parameters are Mu, F prime sub C, and Fy. Note that Mu is obtained from a structural analysis, with a preliminary estimate of the cross-section dimension is used to include the dead weight of the beam in computing Mu. Usually, the design is achieved by assuming an initial value for one or more parameters. Then using the following requirements, the design is finalized. A strength requirement. Mu is smaller or equal to phi Mn. A steel ratio requirement. Rho is smaller than rho maximum. Please note that this requirement is no longer in ACI. However, in practice, this is used as a means to ensure an efficient design with adequate ductility. Minimum amount of reinforcement. AS is larger than AS minimum, where AS minimum is defined by ACI. In most cases, it will be larger of 3 square root of prime sub C divided by Fy times BD and 200 divided by Fy times BD. Or we can simply check if rho is larger than rho minimum, where rho minimum is larger than 3 square root of prime sub C over Fi and 200 over Fi. In practice, alternatively, AS minimum can be taken as 4/3 of the required AS by calculations. And of course, there are detailing requirements to be followed. These are the pertinent references used in the preparation of this video. Basis of design equations. The equilibrium of internal forces and compatibility of a strain across the cross-section make up the basis for design equations. The internal forces and strain diagram for a typical rectangular cross-section is shown in this figure. Here is a cross-section detail, and this is a longitudinal detail. As you can see, the internal forces are shown with a compression force C on concrete and a tension force T in the tension steel. Notice that the strain diagram has a value equal to 0.003 at the extreme compressive fiber, which is located on the compression face of the beam. In this case, D is equal to dt, and X shows the location of the neutral axis. Also, the center of the application of the compression force C is at A/2 from the extreme concrete compression fiber or compression face of the beam. The compression force C is equal to 0.85 F prime sub CBA. T is a tension force, which is AS multiplied by Fy. And from equilibrium, C is equal to T. The moment with respect to the point of application of the compression force, Mn is equal to T times D minus A over 2. From strain compatibility, epsilon T is equal to 0.00 T times dt minus X divided by X. And from ACI, A is equal to beta 1 times X. Beta 1 is equal to 0.85 for prime sub C equal to 4000 psi or lower. For every 1000 psi over 4000 psi, beta 1 is reduced by 0.05. The smallest possible value for beta 1 is 0.65. These equations can be rewritten as follows. A equal to ASFy divided by 0.85 F prime sub CB. The nominal resistance Mn is equal to ASFy times D minus A over 2. Also, if the factor resistance phi Mn is needed, the resistance reduction factor phi must be determined. The smallest possible value for phi is equal to 0.65, and that is when epsilon t is smaller or equal to 0.002. The largest possible value for phi is 0.9, and that is when epsilon t is larger or equal to 0.005. For the values in between the two limits, the middle equation is used. Also, using rho equal to AS divided by BD and introducing parameter M as Fy divided by 0.85 of prime sub C, it can be shown that Mn is equal to rho BD squared times 1 minus rho M divided by 2, which is taken as R times BD squared, where R would be equal to rho times 1 minus rho M over 2. From the above two equations, we can find the following equations. R is equal to Mn divided by BD squared, and rho is equal to 1 over M multiplied by 1 minus the square root of 1 minus 2m R over Fy. We use pounds and inches in these equations. This equation is very important. That makes the basis for design. We're going to repeat this equation throughout this video presentation. Other design considerations. ACI recommends H at least equal to L over 16 for simply supported beams where L is equal to the span length. For a good proportion, we can use B about 1/2 to 2/3 of H. As a preliminary value, D can be taken as H minus about 2.5 to 3.5 inches for most ordinary cases. Clear spacing between bars selected cannot be less than 1 inch or the diameter of the bar, whichever is larger, in the horizontal direction and 1 inch in the vertical direction between layers. The cross-section height h is mostly taken as an even number. The number of bars selected must be symmetric with respect to the vertical axis passing through the cross-section center. As a start, the stirrups can be taken as number 3 bars with 3/8 of an inch in diameter. The maximum bar size that can be used for a beam is number 11 with 1.41 inches of diameter. In this table, you find the bar information. Bar sizes, diameters, and cross-sectional areas are given for number 3 to number 11 bars. Design steps. Step 1. Select the starting size for the beam. Take h at least equal to L over 16 and be about 1/2 to 2/3 of h. Step 2. Knowing B and H, compute the self-weight of the beam as a uniformly distributed load and add it to the dead load and modify Mu. The beam self-weight would be B times H multiplied by gamma in the unit of pounds per foot, where gamma is a concrete density which is equal to 150 pounds per cubic foot. Step 3. Assume phi is equal to 0.9 and we will check it later. Step 4. Assume D as h minus 3 inches, for example, as a start. Step 5. Take Mn equal to Mu divided by phi. This is the required resistance for the beam. Step 6. Compute the parameter R, which is Mn divided by Bd squared. We use pounds and inches in this equation, and the unit for R would be psi. Step 7. Compute rho using the following equation. Rho is equal to 1 over m times 1 minus the square root of 1 minus 2mr over Fy. This is an important equation as we mentioned before. Step 8. Check rho against the minimum value. Rho minimum is larger of 3 square root of prime sub c over Fy and 200 over Fy. However, notice that in practice, alternatively, As minimum is taken as 4/3 of the required As. Therefore, the required As would be rho Bd and 4/3 of that would be used as a minimum. Step 9. Also, it is a good idea to check rho against rho max even though the current ACI does not use rho max anymore. And the equation for rho max is 0.85 prime sub c beta 1 over Fy, the quantity multiplied by epsilon u divided by epsilon u plus 0.004, where epsilon u is equal to 0.003. A typical value for rho max is about 0.021. Please note that this rho max is different from what we call rho balanced. Rho balance is equal to 0.85 f prime sub c beta 1 over Fy, the quantity multiplied by epsilon u divided by epsilon u plus epsilon y. This is called the balanced steel ratio, where epsilon y is the yield strain of steel. Usually rho max is about 75% of rho balanced. Step 10. Select bars for the required As considering the required clear spacing between bars. Step 11. Knowing the bar arrangement, compute the actual value for D. You can use number 3 stirrups and use 1.5 inches of protection cover and 1 inch clear spacing between layers if more than one layer of steel is used. Here is a figure showing how D can be computed when a single layer of reinforcement is used. D is equal to H minus 1.5 inches plus ds plus 0.5 dB. ds is the diameter of the stirrup and dB is diameter of the longitudinal bar. When multiple layers are used, the computation is a little bit more involved. D is equal to H minus E. In this figure, 2 layers of tension steel is shown. 2 layers are shown. The distances E1 and E2 are computed as shown in that detail to the right. And E would be E1 AS1 plus E2 AS2 divided by AS. AS1 is the area of steel layer 1 and the corresponding E1 would be 1.5 inches plus ds plus 0.5 dB and AS2 is the area of steel layer 2 with E2 would be equal to 1.5 inches plus ds plus 1.5 times dB plus 1 inch, which is a clear spacing between the layers in the vertical direction. And we are using inches for the unit. Step 12, knowing the bar size and number of bars, compute the actual AS and then A and X. As we said before, A is equal to ASFY divided by 0.85 prime sub CB, and X is equal to A divided by beta 1. Step 13, compute epsilon T and phi. Step 14, compute the available Mn and make sure phi Mn is larger than Mu. Remember, Mn is equal to ASFI D minus A over 2, and check if phi Mn is larger than Mu. And finally, show a detail of the cross-section design. What if situations? What if rho is less than rho minimum? In that case, use 4/3 of rho BD. What if rho is larger than rho max? In this situation, phi will be less than 0.9, so the factor resistance phi Mn may become less than Mu. Therefore, if possible, the best solution is to increase the beam size. Otherwise, the design is not very efficient. The other possibility is to design as a doubly reinforced section. And the subject of doubly reinforced section is explained in the lesson 11 of this series. Other detailing considerations. Please consult with the ACI code regarding these requirements. The bars are generally cut when they are no longer needed and Mu is reduced. However, bars will need to continue by a distance LD before they are actually cut, where LD is called the development length. Equations for LD are given in the ACI code for various conditions. For crack control purposes, spacing in the first layer of bars cannot exceed the smaller of the following values: 15 inches times 40,000 divided by Fi minus 2.5 C sub C, and 12 inches times 40,000 PSI divided by Fs. We are using inches and pounds. The parameter C sub C is the least distance from surface of bar to tension face, and Fs is a service stress on steel, which can be taken as 2/3 of Fy. Longitudinal skin reinforcement is needed if H is larger than 36 inches and uniformly distributed on both side faces of the beam for a distance H over 2 from the tension face. Maximum spacing of a skin reinforcement follows the above limits, where C sub C in this case is clear cover from the skin reinforcement to the side face. Usually number 4 or number 5 bars are used for this purpose. Bar sizes can be mixed, but the maximum difference is 2. For example, number 7 bars can be mixed with number 5, 6, 8, and 9 only. Let's look at an example. In this example, we would like to design tension bars for a simply supported beam of 30 feet in span, carrying a live load of 1.373 kibs per foot and a dead load of 1.049 cubes per foot. This dead load excludes the self-weight of the beam. We use a frame sub C of 4,000 and Fy of 60,000 psi. For a preliminary size, we use L over 16, which is 22.5 inches as a start. But this is the smallest possible suggested value. So we're going to go a little bit higher. We use 24 inches for H, 2/3 of that, which is 16 inches, we use for the width. Thus we try a 16 by 24 inch section. We use number 3 bars for the stirrups. The self-weight of the beam is 16 times 24, that's the area of the cross section, divided by 144, so we have it in square feet, multiplied by 150, which is density of concrete in pounds per cubic foot. The answer is 400 pounds per foot. Therefore, the total dead load, when we convert these into kibs, would be 1.049 plus 0.4 is 1.449 kibs per foot. The factored load using 1.2 dead load factor and 1.6 live load factor therefore would be QU equal to 1.2 times 1.449 plus 1.6 times 1.373. The answer is 3.936 kibs per foot. Let's find the bending moment. For a simply supported beam, MU is Q L squared over 8. We put QU for Q, which is 3.936, and we get MU. The final answer is 442.8 foot kibs. We assume phi is equal to 0.9. Therefore, the required strength or the required bending resistance is 442.8 divided by 0.9, which is 492 foot kibs. Let's make an assumption of D equal to H minus 3, which is 21 inches. The parameter R, therefore, which is Mn divided by Bd squared, would be 492 times 12,000 to convert the unit in inch pounds, divided by 16 by 21 squared. The answer is 837 psi. Also, parameter M is Fy divided by 0.85 prime sub C is 17.647. Remember the quadratic equation, which resulted into a rho equal to 1 over m times 1 minus the square root of 1 minus 2m r over Fi. We use this equation now to determine the required steel ratio. Plugging the numbers, making sure that the units are pounds and inches, we end up with 0.0163. Let's check rho minimum. Rho minimum is 0.0033. And rho maximum, even though it is not required, but we compute it, and is 0.021. So no adjustment for rho is needed. Our rho is between the minimum and maximum. Required area of steel, therefore, is 0.0163, which is the rho, times B, which is 16, and D, which is 21. And remember, this was our preliminary assumption for D. But at this stage, the required area of steel is 5.48 square inches. There are several possibilities for bar arrangement. We can use 6 number 9, 4 in layer 1 and 2 in layer 2. We can use 2 number 11 plus 2 number 10 all in one layer. And we can check the spacing, is this okay? And of course, the preference usually is to use everything in one layer to get the maximum possible value for D. So let's use this one. Therefore, the available steel based on this design is 5.66 square inches. With this AS, we can compute the value of A. Remember the equation for A. The answer is 6.24 inches, and the corresponding X would be A divided by beta 1, 7.34 inches. Usually, if we have mix of bars, we use a larger size bar to compute D. So D in this case is same as D sub T, would be equal to 21.42 inches. Let's compute epsilon T. By knowing X, from the equation given before, we compute epsilon T, which is 0.0058, larger than 0.005. So our phi value of 0.9 stays. The factor nominal resistance, therefore, is phi mn equal to phi ASFI d minus A over 2. Plugging the numbers there and converting the final values to foot kips, we have 466.1 foot kips of factored capacity, which is larger than mu of 442.8. Therefore, our design is okay. And let's have a cross-sectional detail for our design. Here it is. We have tension steel of 2 number 11 and 2 number 10. We put the 2 number 11 one each at the corner and 2 number 10 at the middle. In the compression area, which is in this case the top, we put 2 number 5 as nominal steel just to keep all the steel in place. And our stirrup right now is number 3. The bar arrangement design is for the maximum bending moment that happens at the midspan. Away from the midspan, the 2 number 10 can be cut and 2 number 11 continued. However, the location of the cutoff point must comply with the resistance of the section for the 2 number 11 bars. Furthermore, the bars must continue for at least a distance equal to the development length before they are cut. Thank you for watching this video.